200 billion stars in the Milky Way. Current estimates put roughly 10% of those as sun-like. That gives roughly 20 billion. Of those, Kepler data suggests about 22% host an Earth-size planet in the habitable zone, the orbital distance where liquid water could exist on the surface. That is roughly 5 billion candidate worlds in our galaxy alone. The Milky Way is 13.8 billion years old. Earth is 4.5. That leaves over 9 billion years during which another civilization could have formed, developed technology, and started broadcasting. We have been searching systematically for over 60 years. The confirmed signal count is 0. That ratio is not simply an absence of data, it is data. In the summer of 1950, the physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory. The conversation drifted to flying saucers, which were in the news that week, and then to the broader question of extraterrestrial civilizations. Fermi, who had a reputation for asking questions that exposed hidden assumptions, looked up and asked, "Where is everybody?" The question was casual. The math behind it was not. If even a small fraction of those billions of candidate worlds produced a civilization capable of interstellar travel or communication, and if even a fraction of those civilizations lasted long enough to spread, the galaxy should be saturated with evidence, probes, signals, artifacts, structures, something. The fact that we see nothing needs an explanation. Europa Clipper is flying toward a moon that may have the right conditions for life. The instruments can test for habitability. But the Fermi question asks something more uncomfortable. If habitability is common, if the ingredients show up wherever the physics allows, then why is nobody home? 11 years after Fermi's lunch, the astronomer Frank Drake sat down at a meeting in Green Bank, West Virginia, with an eclectic group that included Carl Sagan, and wrote an equation. It was never meant to produce a precise number. It was a way of organizing ignorance, of giving the conversation a skeleton so that people could argue about the right things instead of talking past each other. 7 terms, each representing a step on the chain from raw star formation to a civilization that broadcasts detectable signals. The rate of star formation in the Milky Way, known, roughly 1 to 3 new stars per year. The fraction of stars with planets, now known, thanks to Kepler and TESS, to be close to 1. Nearly every star has at least 1 planet. The number of habitable planets per system, estimated at about 22% for Sun-like stars, based on Kepler transit data. Those first 3 terms are measured. The equation starts on solid ground, then it crosses a line. The fraction of habitable planets where life actually arises, unknown. Not uncertain in the way a measurement is uncertain. Unknown in the sense that the mechanism of abiogenesis, the transition from chemistry to biology, has never been observed, replicated in a lab, or detected anywhere beyond Earth. The fraction of life-bearing planets that develop intelligence, unknown. The fraction that develop detectable technology, unknown. The average lifetime of a detectable civilization, completely unknown. And possibly the most important variable in the equation. Drake himself estimated perhaps 10,000 communicating civilizations in the Milky Way. Sagan guessed 1 million. Anders Sandberg and colleagues at Oxford ran a formal uncertainty analysis in 2018 and found that, when honest about the error bars, the probability of being alone in the observable universe was somewhere between 30 and 50%. Not 0, not negligible. The equation does not solve the paradox. It makes the paradox precise. It shows exactly where the uncertainty lives, and the uncertainty lives almost entirely in the biological and sociological terms. We know the astrophysics. We do not know the biology. In 1996, the economist Robin Hanson proposed a framework that moved the question from, quote, 1 to, quote, 2. He called it the Great Filter. The argument is structural. Between dead matter and a galaxy-spanning civilization, there is a series of steps. Each step has a probability of success. The fact that we observe no galaxy-spanning civilizations means that somewhere in that chain, at least one step has a probability close to zero. That step is the filter. The question is where the filter sits. And this is where two versions of the same data lead to opposite conclusions. Version A says the filter is behind us. The hard step is somewhere in the chain we already passed. Maybe it is abiogenesis itself, the emergence of a self-replicating molecule from prebiotic chemistry. Life appeared on Earth remarkably early, within a few 100 million years of the surface cooling enough to hold liquid water. That speed could mean abiogenesis is easy, or it could mean Earth got spectacularly lucky on the first roll, and the apparent speed is survivorship bias. We cannot tell from a sample of one. Or maybe the hard step is the jump from prokaryotic to eukaryotic cells, which took over 1 billion years on Earth. Prokaryotes are simple, ancient, resilient. Eukaryotes are complex, compartmentalized, and they appear to have arisen through a specific endosymbiotic event, where one cell engulfed another and instead of digesting it, kept it as a permanent organelle. That event may have been vanishingly improbable. Or the hard step is multicellularity, which also took hundreds of millions of years. Or the development of a nervous system, or intelligence, or language, or technology. In this version, the silence means we are rare, absurdly, cosmically rare. The chain of events that produced us was so improbable that it effectively happened once in a galaxy of 200 billion stars, and the empty sky is not a warning. It is confirmation that we already passed the hardest test. A recent study proposed adding two new terms to the Drake equation: the fraction of habitable planets with both continents and oceans, and the fraction with long-lived plate tectonics. Their estimate of the combined probability was less than 0.002%. If that estimate holds, it would mean Earth-like conditions are far rarer than the habitable zone alone suggests. The filter is geological, not just biological, and it is behind us. Version B says the filter is ahead. Life arises easily. Intelligence arises eventually. Technology follows. But technological civilizations destroy themselves before they can spread. Nuclear war, climate collapse, resource depletion, engineered pandemics, artificial intelligence that optimizes for the wrong objective function. In this version, the silence is a graveyard. Billions of civilizations rose, peaked, and extinguished themselves in the geologically brief window between developing technology and destroying their biosphere. We are not rare. We are next. The window is worth thinking about. Humans developed radio transmission about 130 years ago. Nuclear weapons about 80. The capacity to alter global climate, arguably, within the last 50. If a civilization typically lasts a few hundred years after developing these capabilities before hitting a terminal crisis, then the galaxy could contain millions of dead civilizations whose signals faded before light from their transmitters reached the nearest neighbor. The universe would be full of ghosts broadcasting into the void long after the broadcasters are gone. And the signals would be too faint, too brief, and too far away for our instruments to detect. Hale finds the silence genuinely unsettling, and that is not a word that comes up often on this channel. Not because the answer might be aliens, because the answer might be us. If version B is correct, then every technological civilization that developed nuclear weapons, industrial chemistry, and planetary-scale energy systems faced the same bottleneck. And every one of them failed. That is what the silence would mean. Not that the universe is empty, that the universe is full of graves we cannot detect. There is a corollary to this that most popular accounts of astrobiology skip entirely. Finding microbial life on Europa or Mars would be terrible news. Not because the microbes are dangerous, because of what their existence would mean for the position of the filter. If life arises independently on multiple worlds within a single solar system, that moves abiogenesis from quote 3 to quote 4, which means the filter is probably not at that step, which means the filter is likely ahead of us, not behind us. Every discovery that makes life seem more common makes our own future seem less certain. Every headline celebrating ___quote _5 would simultaneously be evidence that the Great Filter is something civilizations encounter after they develop, not before. The celebration and the warning arrive in the same data packet. The absence of evidence is not evidence of absence. That phrase gets repeated often, and it is technically correct. But at some point, sustained absence under systematic search starts to exert its own gravitational pull on the argument. We have searched the nearest 1,000 stars for narrowband radio emissions. The Breakthrough Listen initiative has scanned millions of stars across multiple frequency bands. Optical SETI programs have looked for laser pulses. Transit photometry from Kepler and TESS has catalogued billions of stars and found no signs of megastructures, Dyson spheres, or industrial waste heat that would betray a civilization consuming a star's output. The search has real limits. We have covered a tiny fraction of the electromagnetic spectrum, across a tiny fraction of the sky, for a tiny fraction of cosmic time. But it is no longer in its infancy. 60+ years of increasingly sophisticated looking and finding nothing is not proof that nothing exists, but it is a constraint, and constraints in science are data. The Drake equation is sometimes criticized as unscientific because most of its terms are unknown. That criticism misses the point. The equation is not a calculator. It is a diagnostic. It maps where the uncertainty lives. In 1961, every term except the first was a guess. Today, the first 3 terms are measured. The fourth, the fraction of planets where life arises, is the next frontier. And Europa Clipper, the Mars Sample Return Program, and the Habitable Worlds Observatory are all designed to push on exactly that term. Each mission narrows the range. Each narrowing changes the implied position of the filter. This is not a question that resolves into a clean answer. It is a framework for sitting with uncertainty, which is something science does well and public discourse does poorly. The silence is not an absence. It is a measurement with error bars we have not yet shrunk enough to interpret. And the missions currently in flight or in planning, from Europa Clipper to the Habitable Worlds Observatory, are designed to shrink exactly those error bars. But here is what the 2 versions share. Both say the universe is telling us something. Version A says, you are rare, and you should act like it. Version B says, you are typical, and you should be terrified by what that implies. The data does not choose between them. The data sits there, the same for both, and the interpretation depends on a number we do not have, the probability of abiogenesis per habitable planet per billion years. That is one number, one probability estimate, and it may determine whether the silence is a celebration or a warning. The scale of the question is civilizational, but sometimes the answer begins smaller. One robot on a surface, driving a meter at a time for 20 years, sending data back to a species that is still trying to decide whether to listen.